Light is a wave, electromagnetic waves in the spectrum. An electromagnetic wave is different from a mechanical wave. A mechanical wave is caused by a particle vibrating in a medium. So the particles can vibrate up and down, forwards and backwards, but in the end it's caused by particles that move back and forth. An electromagnetic wave, however, is a combination of two different fields that oscillate back and forth. A moving magnetic field creates an electric field, and a moving electric field creates a magnetic field. These two waves create each other, which causes the wave to move forwards. In the end, what makes this different from a mechanical wave is particles are not vibrating up and down, but these fields are. Moving a charge back and forth can create this electromagnetic wave. An important difference between mechanical waves and electromagnetic waves is that mechanical waves require a medium, but electromagnetic waves do not. Mechanical waves require this medium because, again, they are made out of particles that vibrate back and forth, but electromagnetic waves, not composed of particles, do not require a medium. They can travel through a vacuum. The speed of light. All of electromagnetic waves travel at 3 times 10 to the 8th meters per second, but this only applies in a vacuum. In a denser medium, light will slow down. The speed of light in a medium depends on the index of refraction, which is a measure of how much a material slows light down. The closer the index is to 1.0, the faster light travels through the medium. An index of 1.0 indicates that light travels basically the same speed as it does in a vacuum. A higher index of refraction means that light travels slower through the material. The equation we can use to find the index of refraction is n equals c over v. N is the index of refraction, c the speed of light in a vacuum, which is a constant, 3 times 10 to the 8th meters per second, divided by v, the speed of light in whatever the medium is. For example, what is the speed of light in sodium chloride? Now, your reference tables has the index of refraction for a few common materials. We can determine the speed of light using our equation n equals c over v. Now, to solve this, we'll need the index of refraction, which if you look on the right, about halfway down, or 3/4 of the way down, the index of refraction for sodium chloride is 1.54. We can use that as the index of refraction, which is unitless, plug in 3 times 10 to the 8th meters per second as the speed of light in a vacuum, c, and solve for the velocity. As a result, you get a slower speed, 1.95 times 10 to the 8th meters per second. The speed of light in a material will always be slower than the speed of light in the vacuum, so you can use that to check your work. Now, all types of electromagnetic waves are the same thing. They're all electric fields that oscillate back and forth, and magnetic fields that move perpendicular to that. The type of electromagnetic wave just depends on the frequency, or the wavelength, of these fields. So all of these electromagnetic waves that you're looking at are the same thing. The only difference is their frequencies, which gives them slightly different properties. So all of these types of waves, X-rays, ultraviolet rays, visible light, infrared, microwaves, TV, and radio waves, are all electromagnetic waves. Now, since they're all electromagnetic waves, we can use our waves equations to describe them. For instance, an electromagnetic wave is traveling through outer space, which is a vacuum, with this frequency of 8 times 10 to the 13 hertz. What is the wavelength of this wave? Now, we can use our waves equations to describe electromagnetic waves. Specifically, since we have the frequency, and we're looking for the wavelength, an equation with both of those values in it is v equals f lambda. We know the speed of light in a vacuum, or the speed of any electromagnetic wave in a vacuum, is 3 times 10 to the 8th meters per second. We can use that as v. The frequency is given in this problem, 8 times 10 to the 13 hertz, and solving for the wavelength gives you 3.8 times 10 to the negative 6 meters. What type of wave is this? The questions that ask this are looking for the types of waves we just looked at, X-rays, gamma rays, infrared, ultraviolet, and so on. To do this, we can use the table in our reference tables with the electromagnetic spectrum. We can look these up by frequency, which you'll notice are across the bottom of the chart. 8 times 10 to the 13 hertz, well, the frequencies are broken up by the order of magnitude, or the scientific notation exponent that goes with the frequencies. So if you look for 8 times 10 to the 13 hertz across the bottom of the table, you'll notice that it matches up with infrared radiation.